In this video we're going to be looking at logarithms, but before we can deal with logarithms, what we need to have a look at are indices. 16. We know that we can write 16 as a power of 2. So this is 2 raised to the power 4. Now, need to give some names to some of these numbers. So this number here, 4, gets called a number of different things. I've just called it a power. Sometimes it gets called exponent, and sometimes index. So that's the 4. But what about this number? This number doesn't usually get a name, but it does have one. And it's referred to as the base. So, another example might be 64. 64 is 8 to the power 2. So in this case, the 2 is the power, the exponent or the index, and here 8 is the base. So, having got the language clear for indices or powers, what about logarithms? Well, let's see what the motivation might be for wanting to use logarithms. We know, as we've just seen, that 16 is 2 raised to the power of 4. 8, similarly, is 2 raised to the power of 3. Now, supposing we wanted to multiply 16 by 8. Well, one way of doing it would be long multiplication. And we can do that, and the answer is 128. But there is another way. Rather than having to go through this multiplication sum, which, if the numbers were other than 16 and 8, would be very long, can we not make use of the way we've expressed these? 16 times by 8 is 2 to the power 4 times by 2 to the power 3. And from laws of indices, we know that when we do this kind of calculation, what we do is we simply add the indices together. So what was a multiplication sum, we've reduced to an addition sum. Similarly, we could do this sort of thing with division. So if we had 16 divided by 8, that would be 2 to the power 4 divided by 2 to the power 3, and that would just be 2, because we would subtract the indices. Now, if we had a table of numbers where we listed these powers, then all we would need to do is look them up, do addition, and then look back again at what this 2 to the power 7 actually meant, that it means 128. Now, this idea is the whole basis of logarithms. And they were devised in the late 16th century by two mathematicians working independently, John Napier and Henry Briggs. So, what exactly is a logarithm? Let's start with this 16 is 2 to the power 4. This is the power, the index or the exponent, and this is the base. If we take the logarithm, which we usually write as log, to base 2 of this number 16, then the logarithm is 4. This power, index or exponent becomes the logarithm. So we take logs to a base. and it's the base that gets raised to a particular power in indices, and that power becomes the logarithm. So these two are equivalent statements. If we write one, we automatically imply the other. So if I say that 64 is 8 to the power 2, that is exactly the same as saying that the log of 64 to base 8 is 2. These two statements are exactly the same. So if I write a statement down this side, it's exactly the same statement written down here. They both mean the same thing. So that if this side I say the log to base 3 of 27 is 3, what I am saying is that 3 to the power 3 is equal to 27. So these statements down the left here are exactly the same as these statements down the right. So we can write this down as a general statement. If we have a number x, and we can write x as a number a raised to the power n, then the equivalent statement in logarithms is to say that the log to the base a of x is equal to n. And these two are equivalent statements. Let's just develop a little bit of that. Supposing x were equal to 10, then we can write 10 as 10 to the power 1. So if I now take the log to base 10 of 10, then because 10 can be written as 10 to the power 1, then its logarithm to the base 10 must be 1. Similarly, if I had x was equal to 2, then 2 is just 2 to the power 1. And so if I take the log to base 2 of 2, again, that's just 1. So let's make that general. If x were equal to a, then we know that we can write that as a to the power 1. And so that the log to base a of a is therefore 1. And this gives us a general rule that works for any of our base numbers a. Let's see if we can generate some laws of logarithms. We know that there are laws of indices. Can we have similar laws of logarithms? And in one respect, we've already had the first law. So let's have a look. Let's take two numbers, x and y. And what we want to be able to do is multiply x and y together as a general thing. So we say x is a to the power n, and y is a to the power m. Now this statement, x is a to the power n, is the equivalent of saying that the log of x to base a is equal to n. And this statement is the equivalent of saying the log of y, also to base a, is equal to m. We want to multiply these two together. So x times by y is a to the power n times by a to the power m. And what do we get here? A to the power n times by a to the power m means that we add the indices together. So that's a to the n plus m. So what is the logarithm to base a of x, y? Well, quite clearly from the definition we've had, x times by y is a to the power n plus m, so the logarithm is n plus m. But n, we know, is the log of x to base a, the log of x to base a, and similarly, m is the log of y to base a. And so there we have our first law of logarithms, that if we want to multiply two numbers together, we get the log of the product by adding the logs of the two individual numbers. That's our first law. What about our second law? Well, again, let's start with x can be written as a to the power n. Now, what if we take x and we raise it to the power m? That would be a to the n, all raised to the power m. And by our laws of indices, we know that in order to do that, we multiply the n and the m together, giving us nm as the power of a. So what's the logarithm here? The log of x to the power m to the base a equals, well, by definition, that must be this number here, n times by n, n times by m, equals, well, this statement here, its equivalent statement is that the log of x to base a is equal to n. So instead of n, I can write this, and I must multiply it by m. So that's m times the log of x to base a. And there we have our second law of logarithms, that if we want to raise a number to a given power, then we can do that by taking the log, multiplying that log by m. That will give us the log of the number to the given power, and then we can look it up in reverse. So our second law of logarithms. Our third law. Well, in a way, we've already met the third law, because now we've done multiplication of two different numbers, repeated multiplication of the same number. So what we're going to look at now is division. So again, we'll define x to be a to the power n and y to be a to the power m. We'll write down what that means in terms of logarithms. Log of x to the base a is n, and the log of y to the base a is m. And we're going to have a look at x divided by y. So that's a to the n divided by a to the m. And our laws of indices tell us that we do this calculation by subtracting these indices. So that's a to the n minus m. So what's the log of this quantity? Log to base a of x divided by y equals, well, by definition it must be this index here, n minus m. And n is this quantity, the log to base a of x. So log to base a of x. And this quantity m is up here, the log of y to base a. And so there is our third law of logarithms, that if we want the log of a quotient, the log of a division sum, then we subtract the logs of the two numbers that we're working with. One final point, final general point. What happens if we have a to the power 0? Well, we know that anything raised to the power 0 from indices is 1. Well, what does that mean about the log to base a of 1? Well, since we can write 1 as a to the power 0, that means that the log of 1 to base a must be 0. And so the log of 1 in any base is 0. Now that does make sense. Let's just think about it. If you were doing multiplication, 1 times by 6 is 6. Multiplying by 1 doesn't affect the 6. So if we were to do the same in logs, we'd want the log of 1 plus the log of 6. We wouldn't want to change the log of 6 simply because we knew we were multiplying by 1. So it makes sense for the log of 1 to be 0. Let's have a look now at some more examples of calculating logarithms of various numbers to particular bases. So let's take the log of 512 to base 2. Well, this is the same as asking, what's 512 as a power of 2? 512 equals 2 to what power? What's that power up there? Well, 512 is in fact 2 to the power 9. And so by definition, the log of 512 to base 2 is 9. What about the log to base 8 of 1 over 64? This is the same as asking, what is 1 over 64 as a power of 8? Well, what is that? Well, we know that 1 over 64 is 64 to the minus 1. We also know that 64 is 8 squared, 8 times by 8, and so that tells us that 1 over 64 is 8 to the minus 2. And so the logarithm of 1 over 64 to base 8 is minus 2. What about the log of 25 to base 5? Well, this is the same as asking, what is 25 written as 5 to the power? What's that power, that index? What goes there? Well, what we do know is that it's 5 squared. And so the log of 25 to base 5 is just 2. I want to do another calculation which is going to look very similar to this one. And I'll need to compare it with this calculation. So I'm going to repeat this statement over the page. So we've got log of 25 to base 5. We know that that's 2. Now what if I interchange the number and the base? So that I'm asking the question, what's the log of 5 to base 25? Now that's the same as asking, if I have 5, how can I write it as a power of 25? What's that index there? Well, one of the things I do know is that the square root of 25 is 5. And I can write a square root as a power a half. So what that tells me is that the log of 5 to base 25 is a half. And what seems to have happened here is that by interchanging the number with the base, we got 1 over the logarithm. Let's check that by looking at another example. We know that 8 can be written as 2 to the power 3. And of course that means that the log of 8 to base 2 is 3. But what if we interchange the number with the base? So we ask ourselves, what's the log of 2 to the base 8? And that's the equivalent of saying to ourselves, how can I write 2 as a power of 8? What goes there? What's that index? Well, 2 is the cube root of 8, which we write like that. But another way of writing the cube root is to write it as 8 to the power 1/3. And that tells us that the log of 2 to base 8 is 1/3. And so we see again that by interchanging the number and the base, we get 1 over the original logarithm. And that's true in general. I haven't proved it by showing you those two examples, but I have been able to demonstrate it. And that is true in general, that if we have the log of b to base a, then that is equal to 1 over the log of a to base b. Now, we've done a lot of work with different bases. So the question that we might ask is, are there any standard bases? Are logarithms calculated using particular bases? And of course the answer is yes. What are those bases? Well, one of the two common ones is 10. If you look on your calculator, you will see a button that's labelled log, just log. That button that's labelled log gives you logs to base 10. So for instance, if you put in 100 and press the log key, it will give you the answer 2, because the log of 100 to base 10, that's the log of 10 squared to base 10, clearly gives us 2. What's the other common base? Well, the other common base is base e. That's a letter, not a number, you might say. But remember, pi is also a letter, a Greek letter, and a number. And e and pi share something in common. They both have infinite decimal expansions. So e is a very special number. How big is it? Well, to 3 decimal places, it's 2.718. But that's to 3 decimal places. Remember, it's got an infinite decimal expansion. So if you look on your calculator, you will see a button that's got ln on it. And that button ln stands for logs to base e. So if you put the number 3 in it and press ln, it will give you the log to base e of 3. These logs have a name. Sometimes they're called Naperian logarithms, after John Napier, and sometimes they're called natural logarithms. Logs to base e are the logs that get used in calculus. So it is important to know about logs because they're going to come up as a regular part of the calculus, and in particular when we're solving differential equations. So let's see if we can develop a way of using logarithms and see a use for them. This isn't going to be a use in terms of calculus, but in terms of solving a particular kind of equation. So supposing we've got 3 to the power x equals 5. How would we solve that equation? The unknown is up here. It's an index, it's an exponent. We need to get it down, out of being an exponent, down to being an ordinary number. And one of the ways of doing that is to take logarithms. So I'm going to take the log of both sides to base 10. So I'm going to have the log of 3 to the power x is equal to the log of 5. Now notice I haven't written the 10 in on the base. And that's because I'm using the convention that I've just expressed, that log now means log to base 10. Well, I've got the log of 3 raised to the power x. And of course, one of the things that I do know from my laws of logs is that if I'm raising to the power x, then what I need to do is multiply the logarithm by x. Well, now, log of 3 and log of 5 are just numbers, nothing more. So in the same way that I might solve an equation such as 3x equals 12 by dividing both sides by 3, then I'm going to do exactly the same with this, and I'm going to divide both sides by the log of 3. And that calculation can be finished off using a calculator. We take the log of 5, divide it by the log of 3 using our calculator, and get the answer for x. Let's just have a look at one more example. If we have 3 to the x is equal to 5 to the x minus 2. What then? Again, the unknown is x, and again, it's upstairs, so to speak. It's in the index, in the power. And we need to bring it back downstairs to the normal level. So again, we'll take logs of both sides. Log of 3 to the power x is equal to the log of 5 to the power x minus 2. And in the same way, if we're raising to the power, then in order to get the logarithm, we need to multiply the log of 3 by x and the log of 5 by x minus 2. Well, this is now just an ordinary equation. Log of 3 and log of 5 are nothing more than numbers. So let's multiply out this bracket at this side. So we're going to have x log 5 minus 2 log 5. Let's gather together some terms in x and move this as a number over to this side so it's positive. So we're going to add this to both sides, which will give me 2 log 5. And I'm going to take this away from both sides. So x log 5 minus x log 3. I've got all my x's together here, so I'm going to take x out as a common factor. 2 log 5 is x times log 5 minus log 3, and close the bracket. So now to get x, all I need to do is to divide both sides by this number here, log 5 minus log 3, because that's all it is. It's just a number. So let's do that. I'll write the line down again. 2 log 5 is equal to x times log 5 minus log 3. And I'm going to divide both sides by this number. 2 log 5 divided by log 5 minus log of 3 is equal to x. Okay, I've got x. You can put this lump of numbers here into a calculator and work them out. One way of making that calculation a little bit simpler, though, is to notice that here we are subtracting 2 logs. And if we're subtracting 2 logs, that means we are, in fact, dividing 5 by 3 in terms of the numbers themselves. So we can write this as 2 log 5 over log of 5 divided by 3. And that gives us perhaps a slightly better form to do the calculations in. Now, there's one further thing that I just want to have a look at, and this will become quite important when doing calculus. So, let me take the number 8, and I'm going to raise 2 to the power 8. Let me now take logs to base 2 of 2 to the power 8. Well, I know what that is. That's 8. Let's just think what's happened there. We started with a number, we took a base and we raised the base to that power. We then took logs to that base of our resulting answer, and we ended up with the number that we first started with. So in effect, what we did here undid what we'd done there. Now when that happens, what we're saying is we have got inverse operations. That what this operation does, raising the base to the given power, is undone by what this operation does. Does it work the other way around? So, let's start with 8 again. And this time, let's take the log to base 2 of 8. Well, I know that the log to base 2 of 8, well, I need to write the 8 in a different way. I need it as 2 to the power 3. And that, of course, gives me the answer straight away. This number is 3. Now, I take my base number 2 and I raise it to this power 3, and the answer's 8. So again, I've done these two operations in a different order, but the number that I started with and the number that I end up with are exactly the same. So what I've got here are two inverse operations. What one does, the other one undoes. So, in terms of our standard bases, what does that mean? Well, it means that the natural log of e to the x, here I've taken x as a power and I've raised the base e to that power x, and then I've taken the log. The log undoes what I did with the x and leaves me with x again. Similarly, if I have e raised to the power the log of x, this is again x. Because I've used these two processes, these two things again in combination, they're inverse operations, so they must undo what the other one has done. Similarly, if we take our base 10, then the log of 10 raised to the power x is just x. And if we take 10 and we raise it to the power the log of x, then again the answer is just x, because we have undone, by raising 10 to this power, we have undone what we did by taking the log of x to base 10. This is the particularly important one when you're doing calculus. And this is the one that you will need to bear in mind.